The Gambler and the Die That Never Lands. Story by Professor Saad with the aid and assistance of ChatGPT. Narrated by the great Elijah England.
By the way, he's not gonna get any extra credit for this. In fact, if he does a bad job, he's gonna lose credit. Okay.
Chapter 1. The Serpent's Den. On a stormy night, the streets aglow, James the Fox walked in real slow. Through neon lights and whispers dim, he sought a bet, a game to win. Through doors of the Serpent's Den, he entered the lair of luck and sin. Cards were shuffled, dice were rolled, where fortunes rose and fortunes sold. Chapter 2. The Six-Sided Bet. A dealer grinned, his suit was tight. Care to wager? Roll for might? A six-sided die was placed with care. Numbers crisp, a gambler's flair. Roll a 6 and you will be paid. 2 to 1, your fortune's made. James weighed the odds, he thought them fair. He is 1/6 right there. A finite chance, a solid shot. He knew the risks, but still, why not? Chapter 3. The Infinite Die. But then the shadows whispered low. A masked man spoke with eerie glow. That game is dull, I have 1 grand, a die like none you've held in hand. Upon the table, smooth and bright, a spherical die, pulsing light. Numbers ranged from 1 to 6, and all in between, a rolling thrill. James leaned in, his mind intrigued. What's the wager? What's the deed? The masked man grinned, his voice was thin. Land exactly on 6 and you'll win 100 times in. James smirked wide, the bet was grand. $1 million cash in hand. But as he reached to make his throw, his gambler's mind said, wait, go slow. He did the math, he thought it through, then froze midair, his face turned blue. Infinite numbers lie between, so a single roll can't quite be seen. A 6 exists, it must be true, yet landing there I'll never do. I'll roll all night, I'll roll all day, but never land on 6 to play. The masked man grinned, his lesson spun. The bet is lost before it's won. A single number, a hopeless plight, but bet an interval you just might. James smirked, tipped his hat just so, left the die untouched, let the wager go. With a final glance, he turned astride, for a gambler knows when not to ride.
Good job, good job, good job. All right. That was fun.
Was that okay?
Thank you so much, Elijah. I appreciate it. Thank you so much. Okay, you're on record on YouTube too, so people are gonna start extending you job offers now for a voice acting. Okay, so what can you tell from this story? There's a very important lesson from this story. Can you guess what it is? So we finished with discrete probability distributions, and we are headed towards continuous probability distributions. And this example was made specifically to demonstrate a particular claim. What is that claim? So let me guide you through my thought process as I build this example. A 6-sided die has a chance of 1/6 for each one of the sides landing, right? What if I had a 600-sided die? Has a chance of 1/600. What if I had a 6,000-sided die? 1/6,000. 6 million-sided die, 1/6 million. 6 billion-sided die, 1/6 billion. As you take that to infinity, you get a perfect sphere, right? Where each point on the sphere represents a number. We could map them somehow from 1 to 6, but everything in between. So at one point it's 1, at another point it's 1.0000000000001, whatever. an infinite number of possibilities, because there's an infinite, actually uncountable number between 1 and 6. So what's the odds of landing exactly 6? 1 over infinity, right? And that tends to exactly 0. All right, so when we make that claim, as we move from discrete to continuous, if x is a continuous random variable, meaning that it can take on any real value, then the probability of landing any particular value is exactly equal to 0. Now, this is true for any value of x, any experiment you do, any probability, any trial you do. This applies equally to rolling die in a continuous sense, or a continuous roulette, or calculating the probability of a car accident happening exactly at one particular location in the freeway. The probability is exactly 0. Okay, and I will explain why. Started with the single side, with the infinitely sided die, right? So now that makes you wonder, like, can we even do probabilities for continuous variables? Yes, we can. Remember what the masked man told him? He told him, if you pick an interval, you might just win. If you remember that piece in the story. And that's how we're going to define probabilities for continuous variables. So let me give you another example. And this is an analogy. Okay, I'm not teaching you here about masses of metal rods or whatever. This is an analogy to connect the dots between continuous probability and physical intuition. So let's consider a metal rod, okay, the same one we considered in numerical methods, a very thin metal rod for simplicity. So it's practically one-dimensional, okay? It's practically one-dimensional. It looks like this. X starts from 0 to 3 meters, let's say. It's 3 meters long. It's a very thin rod. And we know it has a mass, a total mass of 0.3 kilograms, okay? Across the entire length, the whole thing weighs 0.3 kilograms. Now I'm going to ask you, what is the mass at x equals 0.3 exactly? Not 0.31, not 0.300, 0.3000000. What is the mass at that point? 0. In fact, it's undefined. You can't define a mass at a point. What are you hitting? An electron or a neutron or nothing? It's undefined. You can't define the mass at a point. Okay? You cannot define it, right? So that question is it's a meaningless question. Okay? And that's going to be the same case with probabilities for a continuous variable. You cannot define the probability at a single point. Okay? Now, while we cannot define the mass at a single point, we can certainly define it for any finite stretch of the rod. In the end, the rod, despite the fact that each point has 0 mass, all of them together, they make mass, because there's an infinite number of them. So that's like infinity times 0. It's undefined. In fact, it's a finite number here. Okay? So any finite stretch of the rod, however small that is, has a finite mass. So for example, I could tell you what is the mass of any 1 meter stretch of the rod, assuming the rod is uniform material, right? You could say, well, it's 0.3 over 3. It's going to be 0.1 kilograms. Okay? But still, I would like to describe something about the mass at every point. I cannot plot the mass at every point. Out of the question. So I love plotting things. So if I want to plot the mass of the rod versus the location on the rod, it's going to be 0, flat 0 everywhere. But I still want to say something about the mass of the rod. What if it had inhomogeneous material? What if this stretch weighed 0.1 kilograms, but that stretch, because it had some denser material over here, oh, did I say dense? Density? Okay, so what if this stretch weighed 0.2 kilograms? I still want to be able to say something about the distribution of mass along the rod. Okay? So one clever thing that engineers and mathematicians and scientists do is that we don't define the mass, the volumetric quantity, or extensive property, we call that. We instead define what's called an intensive property, or a property of the material itself. So instead of defining the mass, we define the density of the material. And with the density, you can define the density at a continuum point precisely. And you can totally do that, right? So now when I tell you, if I look at the density of the rod, if it's uniform material, the density could be constant at any point of the rod, right? It might not be constant. It could have a variable, shape because some material is dense over there and less dense over here. And you can totally do that. And you can define it at a point. And then, let's say in this case, it's a constant density. So it's 0.1 kilograms per meter because it's one-dimensional, so it's not per meters cubed. So it's 0.1 kilogram per meter, right? So now we have a density definition, mass density at every point. And then we can use that to infer the mass at any finite stretch of the rod. So still, the mass is still 0 at any point, right? Because there's no length associated with the point. But if we define any finite stretch, then we could calculate using the density, the mass density, we could calculate the mass. So we could say, what is the mass in the stretch between 0.3 and 0.5? That distance is 0.2 meter. Multiply that by 0.1. And you can get the mass for that stretch, okay? This is precisely the same idea for probabilities. Unlike discrete distributions where we said the probability of landing 1 or 2 or 3 or 4, or the probability of 3 successes, 5 successes, we had a factual probability, a numerical probability. In fact, what did we call the distribution? Probability mass function. And I said for continuous, we're going to call it probability density function, because for continuous variables, we cannot define the probability at a point. Instead, we can define the probability density. So now think of probability as mass and probability density as mass density. All right? So that's the biggest jump we're going to do from discrete to continuous. And in fact, remember the probability mass function, that's where it comes from. That's why we call it mass, all right? Because it's finite, it's out of a finite, imagine it's out of finite stretches of this metal rod. You're looking at the mass of only finite stretches of a metal rod. But when you want to look at the continuous distribution of material in the rod, you have to look at the density, you cannot look at the mass. Now, and because for discrete variables, events were countable, even if there are an infinite number, there's a countable infinity of events, you can still count them, and you can still define a discrete probability. But once you go continuous, there's an infinite number of numbers for any continuous random variable. So for continuous random variables, we don't look at the mass, at the probabilities themselves. We look at the densities or probability densities. All right, here are the learning objectives for this chapter. Finally, we're getting into the calculus-related statistics and probability. So by the end of this chapter, so today and Thursday, hopefully, you'll be able to determine probabilities from probability density functions. And just from what you know so far, we will not be defining probabilities at a point. We will be defining probabilities in a range, okay? In a range, plus or minus. And you do that from the probability density by simply taking the area under the curve or doing an integral. That's how we will be moving forward, okay? We'll determine probabilities from cumulative distribution functions. So instead of cumulative mass functions, we will have CDFs now, cumulative distribution functions. You calculate the mean and variances for continuum random variables, understand the assumptions of some common continuous probability distribution. So the same way we did with discrete distributions, we looked at binomial, the Fish distribution, and the hypergeometric. We're going to do the same. We're going to focus a lot on what's called the normal distribution. That's why I've been asking you to put your heights in that spreadsheet, because we're going to plot that and demonstrate that things follow what's called the normal distribution curve. You'll be able to select continuous appropriate probability distributions for certain different applications, calculate probabilities, means, variances. So what's great about having pre-packaged probability distributions is you automatically know their mean and variances. You don't have to calculate them every time. So you have the formula, like nice closed form formula that you can use over and over again and make decisions based on those. We'll go back, if you remember the z-scores that I discussed earlier, you'll understand why we do these z-scores. There's a really neat trick where you can standardize all normal distributions into a single normal distribution that always has a zero mean and a standard deviation of 1. Exactly, the number 1 makes analysis very, very simple. And approximate probability distributions for binomial and Poisson distributions. Okay. For a continuous random process, we define probability densities, like I said. A probability density function, it's a distribution of probability densities. So what is a density? Just like the mass density. The mass density is mass per unit volume. Okay? The probability density is probability, okay, per unit random variable. So your random variable could be length in millimeter, for example. You're taking a measurement of, something over here, right? And you do repeated measurements. Then you have what is the probability of getting this certain range in measurements. Then the probability density would be probability per millimeter. You could be looking at power from a wind turbine. So you're talking kilowatts. Probability per kilowatt, right? So the dimensions, the dimensions of the probability density are always probability, which is essentially 1 per unit random variable. Now connect that to the word frequency that we learned. What is frequency? In hertz, it's 1 over seconds, right? It's 1 per unit time, okay? So that's why we also call these frequency distributions, because they're 1 over unit random variable, right? The same way we call frequency in wave mechanics as 1 over unit time. This is 1 over unit random variable. And this is the formal definition of the probability in for a probability density function or a continuous random variable. So a continuous random variable x would have with it a probability density function, call that f. Then the probability that x is between a and b is the integral from a to b of f of x dx. Remember, if I write p of x equal b, that's equal to 0, always. P of x equal b equals 0 for continuous random variable. Or p of x equal a, it doesn't matter, okay? But a probability for an interval, no matter how small, this interval could be 10 to the minus 6 millimeter between your measurement plus or minus. That's fine. You can define a probability there. Because then what you've done, you've taken the density, you've multiplied it by the length, and then you get a probability. It's like the area under the curve, okay? So this is what it would look like. If your random variable obeys a probability distribution, probability per unit random variable could be watts, could be joules, could be seconds, could be millimeters. The units, the dimensions of this are 1 over the random variable dimensions. Then when you calculate a probability, you pick an interval, all right? Why do we have intervals? That's going to be the case always. You will never ask the question, what's the probability of getting a singular value? You always ask for an interval, the probability for an interval, okay? And that would be the integral. So you're multiplying this distance essentially by all of the probability densities to get the total mass in here. So if this were a mass density, what you're doing, you're counting all of the material in that region, right? Same thing here. We're counting all of the material in this region, multiplying it by their respective probability densities to get the total probability, okay? So in general, this is the definition of a probability in a continuous setting. The probability of x between a and b is the integral from a to b of f of x dx all the time, okay? No questions asked. Now, with continuous variables, less than or equal is really meaningless, especially for an integral. There's no less than or equal for an integral. So in reality, when I say this statement, this is equal to any one of these statements, identically equal, okay? There's no plus or minus, there's no wiggle room here. These are all the same. Typically, we use this just kind of to make us happy, but you can use this as well. They're identically the same. You'll get the same probability. You plug that in the integral, those are all equal, okay? There's no difference between less than or equal or less than. You cannot, in reality, in any device, on any computer, get exactly a number, unless you're doing integers, which means you're doing discrete probabilities anyway. Yeah, question? Yeah, you're just like, yeah, it's cool stuff, okay. All right. Now, what other rules? Let's start kind of putting some law for the land. The sum of all probabilities must be equal to 1. So therefore, the integral from minus infinity to plus infinity of your probability density is equal to 1. So the integral probability density dx is equal to 1. Okay? Now think about dimensions here. This is a dimensionless number, so it has no units, no dimensions. Why? Because this has dimension 1 over random variable units or dimensions times what is dx random variable dimensions. So they cancel out, you get exactly dimensionless number, okay? A dimensionless number. And also one other condition, f of x, the probability density, must be strictly greater than or equal to 0. Strictly greater than or equal to 0. It cannot be slightly negative, okay? It cannot just slightly go below 0, it cannot. It has to be strictly positive. You cannot have a negative probability density, just like you cannot have a negative mass density, okay? Now, this property is also called the normalization property. If you think about it now, this opens up the world for us for all functions in the real space to serve as probability distributions. Polynomials, square roots, logarithms, whatever you want, cosines, sines. But you have to make sure that it is a probability density function or a PDF. And the single condition for that, or it has to be positive, greater than or equal to 0, and the total integral is equal to 1. So that all the probabilities sum up exactly to 1. Okay? So here's an example where you can use this fact to design a probability distribution, probability density function. So suppose I have a process and like I'm plotting probability densities and they look like they follow x e to the minus 4x squared. What is x? It's your random variable. Assume you're like drilling holes in, in metal sheets, and the distribution of errors in your holes follows something like x e to the minus 4x squared times a constant. You don't know what that constant is. In numerical methods, we learned about fitting, data fitting, etc. This is different, okay? So let's say we fit it, but we still need to normalize it. We still need to make sure that this is a probability density function. How do you find k, this parameter, k? Well, we use that property that the integral needs to be equal to 1. Okay, so choose k that this is a PDF, such that this is a PDF. So obviously, must satisfy f of x greater than or equal to 0, and the integral over the infinity is equal to 1. From the first condition, it's obvious that k has to be positive because x e to the minus 4x squared is positive because x is positive there. So k has to just be positive. And then the second condition, we find k. So you plug this f of x into the integral. You set it equal to 1, and you get k over 8 equal to 1. So k is equal to 8. So now if you put k back in that distribution up there, it becomes a probability density function. It can serve as a probability density function. In the end, it might not be truly representing the probability densities of your system, but if it does, you need to make sure that it's normalized. In other words, the summation of all probabilities is equal to 1. All right, some other rules. And again, less than or equal are the same here. So probability of x less than b equal to probability of x less than or equal to b. And that's equal to the area under the curve from minus infinity to b. Okay? The probability of x greater than or equal to b or greater than b is the integral from b to plus infinity. So when I don't specify the range, the upper bound, if I'm only specifying the lower bound or specifying the upper bound, the other bound is either minus infinity or plus infinity. Okay, so you're computing the area under the rest of the curve. All right, let's do an example. Let the continuous random variable x denote the current measured in a thin copper wire, and I promise you'll do some more engineering examples, okay? I picked the worst subject that I like is electronics, but it's okay. Let the continuous random variable x denote the current measured in a thin copper wire in milliamps. Okay, so assume that the range of x, so the range of milliamps is between 4.9 and 5.1 milliamps. So the range of current is, range changes based on power fluctuations, etc., and consumption and needs for the device you're looking at. It ranges between 4.9 and 5.1 milliamps. and assume that the probability density function of x is f of x equal 5, okay, between 4.9 and 5.1. So it's 0 elsewhere, but it's exactly equal to 5 between 4.9 and 5.1. Okay? 4.9 and 5.1. What is the probability that a current measurement is less than 5 milliamps? Okay? So let's look at this. This is what the probability density function looks like. It's just a constant, and it's only valid between 4.9 and 5.1. Agreed? Okay. So now, and you can double check that this is actually a PDF, because the integral from 4.9 to 5.1 is 0.2 times 5, which is exactly 1. Okay. Now we're looking for the probability that x is less than 5, so we want this area here. It's the integral from minus infinity, which is 0 everywhere, until 4.9. So from 4.9 to 5 of f of x dx gives you the probability to be 50%. Okay, exactly 50% for the current being less than 5 milliamps, measuring the current being less. Okay. Now what are the units of this PDF? 1 over milliamps, right? 1 over milliamps. It's a probability density. Okay, another example. Let the continuous random variable x denote the diameter of a hole drilled in a sheet metal component. So you're building sheet metal components for a car, and you're drilling holes in them so you can mount them. We're targeting a diameter of 12.5 millimeters. Now, most random disturbances, so you're like holding the thing, and sometimes the drill bit kind of tugs on you, and you just kind of start moving and vibrating, etc. So you cause some error. So most random disturbances in the process result in larger diameters. So over the years, historical data show that the distribution of x can be modeled by the PDF, this PDF, 20e to the minus 20x minus 12.5. So they collected data over the years. They tried to do an observational study to collect probabilities, right? And they came up with this probability distribution PDF model. As long as x is greater than or equal to 12.5, everywhere else it's 0. Okay? Everywhere else is 0. So now the question is, if a part with a diameter greater than 12.6 millimeters is scrapped, what proportion of parts is scrapped? So in other words, what they're saying, okay, let's say our tolerance is anything above 12.6 millimeters, we're going to throw it away. Okay, so now we're asking, in this production, how many parts are being scrapped? In other words, what's the probability of getting 12.6 or more, okay, in our holes, right? Okay, this is the probability distribution. It's 0 everywhere, PDF, and then 12.5 goes up to this whatever value, and then goes down to infinity. We're asking, what is the probability that these holes are greater than 12.6? Because our tolerance is, what, 0.1 millimeter here. We're going to say anything more than 12.6, we're going to throw it away. Okay? So now we're asking, what's the probability that we're going to get more than 12.6? And it's going to be a fraction, a percentage, a proportion. And you get 13.5%. So you just integrate that distribution from 12.6. In this case, you need to go to infinity, right? Because it has infinite support. And you go to infinity and you get about 13.5%. That's a lot. 13.5% of your metal being scrapped, melted again. It's an energy. It's bad. You need to revise your process. Okay. I would say maybe a 1% error material would be acceptable, but no company is going to accept 13.5%. So what are the units of the PDF here? 1 over millimeter. Okay? 1 over millimeter. All right. Now we're repeating things like we did with discrete, but the meanings are going to be different. Cumulative distribution function, CDF. So for a continuous random variable with a PDF f of x, so now every time we say continuous random variable, you associate with it a PDF or a probability density function. We also define the cumulative distribution function, or also referred to as CDF, as opposed to CMF for discrete. We denote that by capital F. Great nomenclature, right? Because it's a And it measures the probability that it's the same definition as we had for the discrete case, that your random variable is less than some specific value. So in other words, it's taking the integral from minus infinity up to the point of interest. Okay? And it's defined as f of x, capital F, is the probability that your random variable, capital X, is less than or equal to a specific value. And that's equal to the integral from minus infinity to x of f of u du. Okay, so this is your PDF. I chose different variable names here because this integral is going to end up in x, so that we have a generic formula for the cumulative distribution. I want to be able to say, what's the CDF of 5? So that gives me the probability that x is less than 5, right? So that 5 is going to come in here, and then you just plug it into the formula. We'll do these integrals sometimes numerically, but oftentimes analytically, okay? And you have a formula for that, all right? And x is anywhere between minus infinity to plus infinity. So we're going to go back to the current in the copper wire example, and we're asked to find the CDF for that. And remember, the PDF was constant. It was 5 for x between 4.9 and 5.1, and 0 everywhere else. So that's the PDF, okay? Now, our CDF is going to look like this because I did the integration previously. And so in this case, the CDF has 3 parts. The CDF is equal to 0 for x is less than 4.9. Okay? Actually, this doesn't match this. My apologies. It's for a different curve. But it's going to look similar. The x-axis is off here. So x is equal to 0 for x less than 4.9. Okay? And then between 4.9 and 5.1, you do the integral of f of x. Remember, you're integrating from minus infinity, but minus infinity to 4.9, it's all 0, so we don't care about that. So we're going to start from 4.9 to some arbitrary point x that's less than 5.1 here. And then you do the integral, and you get a formula for your cumulative distribution. So now when you ask f of 5.1 or 5.01, you just plug in 5.01 here, and then you're going to get the probability that your random variable is less than 5.01. Right? You get that formula. It's a straight line, right? Because the integral of a constant is going to be a straight line. And then everywhere greater than 5.1, your cumulative is equal to 1, not 0. Because remember, the cumulative is the integral of all the probabilities before, the sum of all the probabilities before that point. So once we go outside 5.1, all the probabilities are going to be exactly 1. The cumulative probability is going to be 1. All right. We do this for the drilling operation as well. Recall, we had that 20 e to the minus 20 x minus 12.5. It's okay if you want to use your symbolics on your calculator or Mathematica on your homework. This is not a calculus class. It will be useful if you know what you're doing with your integrals. So if you don't, you have no chance in figuring it out with Mathematica because it might give you a wrong answer. You're going to think it's okay. So I trust that if you're going to use those tools, you know what you're doing, right? If you want to do it by hand, great. Most of them are simple enough. You're going to do them by hand, but you're okay if you want to use any help from the World Wide Web. Okay, so that's the PDF in this case, and once you integrate it, it's going to look something like this. So in this case, the PDF has 2 parts, right? The one over here, the CDF, it's all 0, and then it's going to be a different formula over there. So for x less than 12.5, the CDF is 0. There's no probabilities over there to accumulate. And anywhere after 12.5, you do the integral from minus infinity to x, but from minus infinity to 12.5, it's 0, so it doesn't matter. So we start from 12.5 to x, and you do the integral, and you get this formula, which is this guy, 1 minus e to the minus 20, for anywhere x greater than or equal to 12.5 or greater than 12.5. Again, what this means, the cumulative, so if I tell you what's the probability, what's the cumulative at this point, is going to be equal, you just plug in this point here, let's say 15, is going to give you the area under just the whole thing over here, okay? Or the area, this area, it's going to give you this area, okay? It's a single point on the CDF, but every single point on the CDF is in semi-infinite interval from minus infinity to that point, okay? Calculus is cool. Just wanted to say that. Do you think calculus is cool? Yeah? No? Okay, look what we can do with calculus. How many fundamental theorems of calculus have you heard of? I've heard like 17 fundamental. Like, this is the fundamental theorems. Like, okay, how many of these fundamental? So they're all fundamental theorems. This is another fundamental theorem of calculus. In that, okay, if you have, not specifically for CDFs, any integral that looks like this implies that the probability density function is nothing more than the rate of change of the cumulative distribution. That's insane. Well, really? It's not that insane. Because the cumulative distribution is like mass. And the density is mass per volume, or the rate of change of mass per volume. This is what this is telling us. Now, why would we do this? Because sometimes it is easier to calculate cumulative distributions, cumulative values. So if you have a formula or a model for your cumulative probabilities, you can infer your PDF from those by taking its derivative. Okay? Very useful tool. Here's an example. A lot of engineering examples today. Good. So I'm on your good side now. Okay? The time until a chemical reaction is complete in milliseconds is approximated by the following cumulative distribution function. 0 for x less than 0, and this formula 1 minus e to the minus 0.01x for x greater than or equal to 0. Okay, so now we're calling our random variables x all the time, but it could be time, it could designate distance, could designate temperature or pressure. We just standardize it by calling it x on the x-axis, but you're welcome to also use different nomenclature. I will be using different nomenclature as we eventually, I think. Okay, so now they're asking, determine the probability density function of the random variable x, all right? So it's simply the derivative of this, so df by dx. For x less than 0, it's 0. There's no probability densities before that. And for everywhere greater than 0, you just differentiate this guy, you get minus 0.01 times minus 1, you get 0.01, e to the minus, etc. Okay, so now you have the PDF, okay? And then they ask, what is the proportion of reactions, or what proportion of reactions is complete within 200 milliseconds? In other words, okay, starting from 0, when the reaction started, up to 200 milliseconds. So in other words, what is the probability that your reaction time is less than 200 milliseconds? That will give you the proportion of reactions that would be completed within 200 milliseconds. That's nothing more than the cumulative distribution at 200, right? We have that. You plug in 200 into that formula, and you get 86.5%. Okay, so you say, well, yes, probably almost mostly done. Okay, 86 is a vast majority. All right? Okay, now, I want you to put statements like this in your homework. Like, imagine in this slide, imagine I have f of x, df of, and just nothing. Nothing else. You wouldn't accept that. You would come and say, you'd go and say, Professor Saad is not having enough information on his slides to teach us. Okay? They will fire me, I'd lose custody of the kids and then be deported, right? So, I'd like you in your homework assignments to add some more information, please. Okay? I've instructed my TAs to give you more feedback on that. Actually, I'm going to instruct them after this class because this just occurred to me. You are engineers. I don't care if you do it for this class or not, but the reason I ask you of it is to get it in your habit, no matter how annoying you might find it, get you in the habit that you are going to produce at least readable reports for people, not just numbers. We already have a bad reputation as engineers that we just are geeky, right? So let's fix that, okay? We can still be geeky, but add some text to it, please, okay? All right. So today it's a lot of jokes today and stuff. Okay, so don't be mean. Make more than a difference. Make a variance. Okay. Ha ha ha. All right. So with the probability density function, we can define means and variances. Okay, obviously that's what I mean by mean. Okay, so the mean or expected value, in the discrete case, it was a summation of x times the frequency distribution. In this case, it's going to be the integral over the entire space, from minus infinity to plus infinity, over all possible random variable values of x, f of x dx. That's nice, kind of nice, well-rounded, continuous integral. We call that the expected value or the mean value. We put mu because we're dealing with populations, okay? Similarly, for a sample, it's going to look the same. The variance now, sigma squared, going to look also the same. Instead of a summation, we have an integral. The same as the discrete case, but we have an integral also from minus infinity to infinity. And remember, the variance measures the average distance from the mean value, okay? So you have an x minus mu, the mean value computed above, squared times f of x, and this is identically equal. So if you take this integral and split it, if you do the power law here, so x squared minus 2 mu x plus mu squared, and you plug it in here, you get this formula too. Sometimes it's easier to do this. If you've already computed this, you don't want to compute it here again, doesn't matter. But they're identical. This gives you the variance. We know what the variance roughly means. It has dimensions of random variable squared. Don't forget that. So I was going through 3 textbooks for this lecture. So the textbook you have touches on some topics. There are other textbooks that touch on some other topics. And the shock I had that in 2 of the other textbooks, they had the mistake of calculating the variance for energy and putting it in joules instead of joules squared. Okay? So yes, I caught a mistake on that. Anyway, so be careful. The units of variance are random variable squared. And the standard deviation is the square root of sigma squared. Okay. Now, I want you to consider the following. So we're going to take these formulas. Calculus is really cool because it just expands the possibilities of what you can do with things. So I want you to start now. I want to look at the pattern in these formulas. You see there's there x f of x integral. There's x squared f of x integral, or x minus mu squared f of x integral. There's something interesting going on. So let's see what it is. So I want you to consider the following. I'm going to take these 3 things that I just mentioned, which we saw previously. One of them is the mean. This is the variance. This is a piece of the variance, right? The integral of x squared. Now notice these things here. In fact, you can put anything you want over here. It doesn't have to be x squared. It doesn't have to be x minus mu squared. It could be x cubed. It could be square root of x. It could be exponential of x. It could be whatever you want. It could be, in general, a function of the random variable itself. It could be a function h of x of the random variable. It's like enough with more functions. Well, it's going to be pretty powerful when we have functions of random variables and that you're going to need to put in there. So we call this, in general, this integral. So remember the expected value, we put e of x, and it was the integral of x, f of x, right? Now we're going to do e of h of x, where h is some arbitrary function of the random variable. Okay? And we call this the expected value of the function of the random variable. All right? You can put anything in there. Now, why on earth would we need that? Well, I'm glad you asked. Let me give you an example. In wind energy systems, again, an engineering example, you ask for it, you're going to get it. Okay? Such as wind turbines, wind speed is a random variable. It varies a lot. It's unpredictable. So it is a random variable, and it's continuous. Sometimes it's 0. Sometimes you're barely kind of holding on to dear life, right? So it varies a lot, especially at the higher altitudes of these wind turbines. Now, the power output of a wind turbine is a nonlinear function of the wind speed. Okay, and that is given by some constant times the speed cubed. Okay. Now, v is the wind speed, k is some constant, whatever it is, depending on the turbine itself. But v is a random variable, so is v cubed, right? And so, therefore, is the power. So the power is also another random variable. But I suppose that the information you have about the probability distribution, or the PDF, is only on v. Not on v cubed, not on p. It's only on v. Now I'm interested in the mean value of the power of this turbine. I don't care about the mean value of the wind. I mean, I could care about it, but how can I compute the mean value of the power? Is it the mean value of the velocity cubed? So I have the PDF for the velocity, and I can compute the expected value of the velocity, the mean value. Now the power is velocity cubed. Does the mean value of the power equal to the mean value of velocity cubed? Absolutely not. Okay? The mean value of the power is the mean value of v cubed, and it's not equal to the mean value of the velocity cubed. Okay? So this is an example where h of x is kv cubed. So we need to define those formally. That, yeah, if you take a random variable, make a function of the random variable, in this case it's power, kv cubed, then you compute the expected value of that variable, and it looks, let's just say, that same integral. Okay, here's another example. In wireless communications, signal strength fluctuates to what's called fading, or just kind of the signal fades, as if we need any more trouble with internet connections. Okay, where signals travel along different paths and interfere constructively or destructively. Now, so you're watching Netflix, someone else is watching Voodoo, and your kids are playing Minecraft, and signals are coming in through the router, they cross path. You end up seeing Minecraft, and your kid sees nothing. So anyway, so signal crossing wires, right? A model for this looks like as such. The signal received is equal to the signal transmitted times a phase shift, a cosine theta. And theta is the angle between those, the phase shift between those frequencies. This is beyond what we know, but this is the model. Now, theta is a random variable. Theta itself is a random variable. Obviously, cosine theta is going to be a random variable, and therefore, the signal received is going to be a random variable. The signal transmitted is not a random variable, because I'm sending a picture. It's not a random variable. But because of theta, I'm going to receive some aberration in my received signal. So the received signal is going to be a random variable now. What's the expected value of the signal loss? Well, it's the expected value of the signal received equal expected value of S transmitted times cosine theta. Now, S transmitted is constant, so it comes out of the integral. So you have the expected value of the received signal is the signal transmitted times the expected value of cosine theta, not cosine of the expected value of theta. Be very careful. Okay, and this is not equal to S transmitted cosine of E theta. Okay? So you can't say that the expected value of the received signal is cosine of the expected value of theta. That's wrong. It's the expected value of cosine theta. It's a grave mistake. Okay? All right. Let's take a moment. All right. Let's resume. And this time it's actually going to be a pun joke. Let's take a moment. All right. So does that resonate with anyone taking physics now? Moment of inertia. Okay, so let's take a moment and understand when moments come from, like moments in life and in math. All right, so there are a few special cases for h of x. Obviously, h of x in that expected value, you can, put it, do anything you like with it, depend, like the examples we saw. But for the specific cases where h of x was equal to x or x squared, looks like there are a few useful cases for specific values of h of x. So in general, when h of x equal x to the power k, those have very meaningful properties of probability distributions. So when k is equal to 0, you have the integral of f of x dx. What is that? That's equal to 1. That's the condition for the PDF, right? When k equal 1, you have the expected value, the mean value. Okay, great. When k equal 2, you have something related to the variance, right? It's part of the variance formula if you separate mu squared out of it. And you can continue, and each one of the k values has a different meaning. I'll give you just the next one. When k equals 3, you get the integral of x cubed f of x. Guess what that describes? we're going to see later that this describes the symmetry of your data. Depending on the value of that integral, you can tell if it's perfectly symmetric or if it's skewed to the left or skewed to the right. Okay? And then you can do x equal 4 and so on and so forth. Okay. Now, in general, the expected value of x to the power k, in other words, when h of x is equal to x to the power k, that's referred to as mu sub k. And they're called the moments of the distribution. Or mu k is called the kth moment of the distribution. You can laugh now, please. Thank you. Thank you so much. Thank you so much. Okay. All right. When only one person laughs, reminds me of like my mom trying to support me. I'm like, thanks, mom. You know, nobody else laughed, but thank you for the support, regardless. So I appreciate the support. Okay. Okay. So now, speaking of support, the values on the x-axis where the PDF is defined is called the support of the PDF. I didn't define it here. It's not necessarily important. But in math lingo, the x-axis, the values on the x-axis where it's defined is called the support. Okay? You could say a function has a semi-infinite support, so it's defined from 0 to plus infinity or minus infinity to 0, or like an infinite support or like a finite support. All right. Now we can also define what we call the central moments. If you remember, the variance formula was defined with respect to the mean value. You can do the same for any value of k, and instead of h of x being x to the power k, h of x becomes x minus mu to the power k. So we call those the central moments or the kth moment with respect to the mean value. Okay, with respect to the mean value. The kth moment with respect to the mean value. So when k is equal to 1, you should get the mean value, but in this case, it will be 0. So the central moment, the central first moment, where k equal to 1 is equal to 0, because it's with respect to the mean value. So you get mean value minus mean value equals 0. We'll look at those mathematical properties, as in some of the homework assignments. Okay, so now it's time to look at a few distributions. Who likes uniformity? When I think about uniforms at school for my kids, I like it. It's simple. It's just one uniform. There's a few color variations, but no, I want to buy an Air Jordan that's cost like $1,000 or whatever. It's not allowed. You're just wearing these clothes. They look the same. There we have 7 pieces, 7 pants, 7 shirts. You wear one each day and you're done. No differences between the kids and whatever. And so I think it's helpful. So in a sense, I like uniformity that way. Uniformity of my slides. They look the same across courses. They look the same across different lectures. Helps establish a pattern, right? And with distributions, the simplest distribution we can define is a uniform probability density function on the interval, on a finite interval a, b, and it's given by 1 over b minus a when x is between a and b, otherwise it's 0. So it would look like this. Now why does the value have to be 1 over b minus a? Because the sum of all probabilities, or the integral, needs to be equal to 1. So think about it. The integral, or the area under this curve, is b minus a times the height, which is 1 over b minus a, so that gives you 1. Okay, so that's why the value of a uniform PDF is 1 over b minus a, that interval. So in a way, that value is defined by the interval itself. Okay? All right. And it's 0 otherwise. Immediately from this, you can calculate the mean value, which is a plus b over 2, the variance, b minus a squared over 12, and the cumulative distribution, x minus a over b minus a, when x is between a and b, and 0 otherwise. Okay? So those will come in handy. Those formulas will come in handy when you're doing homework, etc. So here's an example. An electron emitter produces electron beams with changing kinetic energy that is uniformly distributed between 3 and 7 joules. So now we've given you a and b, right? A is 3 and b is 7 joules. So you immediately know the value of that PDF is 1 over 7 minus 3, or 1 over 4. Okay? So that's automatically given. And then we have a bunch of questions. What's the mean kinetic energy? What's the variance of the kinetic energy? What's the probability that an electron beam has a kinetic energy exactly 3.2 joules? And the last two questions, I'll do them on the next two slides. So we can hit this just very quickly. So first we build the PDF is 1 over b minus a, which is 1 over 7 minus 3. Okay, the dimensions, what are the dimensions? 1 over energy, 1 over joules, okay? And between 3 and 7 and 0 otherwise, okay? That's your uniform PDF. The CDF is x minus a over b minus a, so x minus 3 over 4, again, defined for that. And the mean value is a plus b over 2, so 3 plus 7 over 2. The variance is b minus a squared over 12. That's the mistake in those textbooks. They had 4 over 3 joules, which is wrong. Okay, it's joules squared, the variance. So the standard deviation is 2 over square root of 3 joules. Okay? And then finally, the probability that x is equal 3.2 joules exactly, what is that? 0. 0 with confidence. No trick question. You cannot define a probability at a single continuous point. It's a meaningless question. The probability is 0. There's an infinite number of points, okay? Think of the infinite-sided die in the great example that our great Elijah narrated for us, right? Okay. Now, if we can change the upper limit on this beam, okay, so we can change b. So suppose a is fixed, we're still at 3, but we can change b, the upper limit on this beam, so we can, put in more energy into the system. What should be the upper limit? What should be that b value so that the mean kinetic energy is 8 joules? So in the previous case, the mean kinetic energy was 5 joules, okay? Now, we want it to be 8 joules. So what should be b? So the mean, in this case, we have 1 over b minus 3. So we don't know what b is, right? But the mean value is 3 plus b over 2, so a plus b over 2. And we want that to be equal to 8, so we can solve this and get b equals 16 over 3. All right? A great way of using these formulas to ask inverse questions. Okay? I want my mean kinetic energy to be 8. How do I adjust my controller? Just from knowing the idea of the probability density function. Okay. Another example, if we can change the upper limit of this beam, what should be the upper limit so that the variance decreases to 0.75? Previously, joules squared. Previously, it was 4/3. Okay. Now we want it to be 3/4, right? So 0.75. Okay. So again, we start with this, but now we have the formula for the variance: b minus a squared or b minus 3 squared over 12 equal 0.75. You solve for b, you get 2 roots. You pick the root that is physically makes sense, and that's equal to 6. Okay. Good. That's the uniform distribution. It's used to model like uniform events. Well, not really, because the probability density is uniform, right? The probability density is uniform, not the probabilities themselves. The probabilities are defined over an interval, okay? And you have to integrate that, and then you're going to get a straight line. All right, who wants to be normal? Nobody wants to be normal. Okay, well, unfortunately, they call it the normal distribution. And like, not because it's perpendicular to something, like in math, I would imagine all the nomenclature to be mathematically specific. Like normal means perpendicular, diverging means the cross product means something, right? Except in this case, normal actually means typical. That's kind of how they picked the name for it. Just a normal distribution. We see it normally everywhere, okay? There's a beautiful story behind the normal distribution. Have you heard of the normal distribution before? Okay. Have you seen it in a mathematical context? Okay. What do you know about it? I was researching it literally yesterday and today, and from things I thought I knew about it and just wanted to confirm. Okay. So we kind of know, it's a bell curve, looks like a bell, bing, bong, right? So maybe they designed these church bells based on the normal distribution. But you probably heard that things in life are generally follow a bell curve, surprisingly, incredibly. Like collecting heights of students. So we're going to show that it's actually so great. You go and plot that histogram. It looks exactly like a normal distribution. I love it. And you are a small sample of the university, and you're all distributed normally. So this is great. Good example. It worked. Like if it's not going to work, I'm just not going to do it in class. But it worked. So things in life happen to be distributed normally. And what does that mean when we say they're normally distributed? So our heights, so we'll take the heights example. Height is a random variable across people because, you know, I cannot predict your height. There's 1,000 parameters that go into a person's growth, right? Nutrition, they were a kid, if they fell, if they broke a leg or an arm, if nutrition deficiencies, overnutrition, whatever, like weather, travel, all sorts of things, right? And, you know, so as far as we know, height is a random variable and a continuous one because height varies across the population continuously. You could be 164 centimeters, 164.1, 163.8, 220 centimeters. Whoever put that number, I'm going to have a talk with you. I don't know who you are, but you shouldn't doctor data. Anyway, so we'll talk about that on Thursday. However, things are normally distributed. What does that mean? The height is as a random variable. We will say that it has a probability density from which we can calculate the likelihood that you are in a certain height range. It has a probability density that looks like that normal distribution, which looks like a bell curve. We'll discuss it, but that's what it means when we say a variable is normally distributed. Your hat sizes, they're going to be normally distributed. Your, distance from thumb, some thumb length over your height. Specifically in measurements, it's surprisingly incredible the fact that you go take measurements in a lab, pick anything, and take repeated measurements. Have someone else do it. Collect the data and plot a histogram. The data will be normally distributed. You didn't even doctor anything. You just took measurements. You will see that the data is normally distributed. There's a fundamental property in nature. Turns out that things are normally distributed. In fact, there's a math theorem about that. So it is one of the most important distributions in statistics and math. The first person who discovered it formally and published it was Abraham de Moivre. He was looking at the binomial distribution, and mathematicians have nothing to do but just take things to the limit. So he's like, what can I do with a binomial distribution? He started making n larger and larger and larger and larger and plotting frequency distributions. And he showed that the x factorial, if you replace that with what's called Stirling's formula, which is a continuous approximation to the factorial, you get a bell curve. They didn't know what it was called. They didn't call it the bell curve. Now we call it the normal distribution. But in his published paper, it always converges to the special curve, and he called that and moved on. At the same time, scientists, and this is kind of what I refer to the measurements, to an astonishing degree, scientists across different countries in Europe, they observed that repeated measurements are distributed according to that same distribution that de Moivre discovered. And like, what the heck? So they called it the normal error curve because, all the errors were distributed on average. They look normal. Things look normal like that. Then epidemiologists and other kind of medical people came in and started seeing same things with height and other things. Just 1 minute before you go, okay? Gauss, of course, Gauss is everywhere, and Euler. He rediscovered the normal distribution when looking at errors in astronomical data. Again, goes back to error. And that's why it's called the Gaussian distribution. He wasn't really the one who discovered it, but we call it Gaussian, but also refer to it as the normal curve. But the guy who made a big difference in it, and I'll let you go after I state this, is Pierre Laplace. So the Laplacian, the del squared operator, he finally discovered what others did not see, that what he discovered is foundational in statistical theory. It's called the central limit theorem. And it's exactly what I described, that everything, if measured repeatedly, and you've taken an average of that repeated experiment, I'll give you a specific example, then all of those averages are distributed normally. Anything. Could be any experiment you're doing, any measurement you're taking. So I'll give you an example. So you roll a die 100 times. That's one experiment. You roll it 100 times. Then you take the average of all outcomes. First one is 1, second is 6, etc. You add them all up, divide them by 100. That's one experiment. You take that average value. Okay? Take that average value. Now repeat this experiment 1,000 times. So roll the dice 100 times, another 100, another 100, 1,000 times. Take the average, plot the averages, they will be normally distributed. It's insane. Anything you do is normal. It's called the central limit theorem. Netflix uses the central limit theorem to predict what you're gonna like next, what movie you're gonna like next. Okay? read Naked Statistics if you have some time to read like a fun read. They explain the Netflix algorithm and how it detects, and it's surprisingly precise. Now, why do we average? We average all the time. If I'm taking measurements of airflow in a room here, I'm going to repeat the measurements a few times, then take an average. Someone else comes and does it, they take an average. Those averages are going to be normally distributed. Okay? So they're everywhere. All right. Godspeed. See you on Thursday.